Alright, and so what I want to talk about in this video is reaction equilibria, and specifically what determines if a reaction has reached equilibrium, right? And so we know that equilibrium just means a state or condition in which the properties of your system or your mixture don't change, okay? And so we've applied that to non-reacting mixtures, but now we want to do that for mixtures in which there are reactions going on and bonds are breaking and being made. All right, and so how do we define that for those types of systems? To help identify what the criteria are, what we're going to do is we're first just going to consider a couple of model systems. And so we're first going to consider a reaction in a constant molecules, volume, and internal energy system. Okay. In your reactor design course, this type of reactor would be known as an adiabatic batch reactor. Okay. Where you could picture it like this. So I have a square with some insulation around it. And reaction mixture is inside. Okay. All right. Now, if you remember from our previous discussions, or at least back in Chapter 7, when we talked about a constant NVU system, for this sort of system to reach equilibrium, what had to happen is that the entropy of the system, or S, is maximized. Okay? Okay? Alright, and so somehow we want to figure out a way to formally identify when entropy in the system is maximized. Okay? And so what we're going to do is we're going to basically write this in terms of the fundamental equation of entropy. To do that, I'll first actually just start with the fundamental equation for internal energy for a mixture. And so du is equal to T ds minus P dV. And so this is the term for the pure species. Or maybe not even the pure species, but the entire mixture. But then, since we're dealing with mixtures, we also need terms that account for the different species in the mixture, right? And from Chapter 8 and Chapter 10, we know that that term is going to be the chemical potential of each species, dNi. So this is a mixtures term. All right, but we want to rewrite this equation in terms of entropy, so we just rearrange it. What we get is that ds is equal to 1 over T du plus P over T dV minus mu sub I dNi. Okay? So this is the fundamental equation for entropy when you're dealing with mixtures. Now, we're looking at a constant NVU system, so that means that the du term is 0, and also the dV term is 0. So all we're left with is negative mu I dNi. Okay? And so this is our equation for now. But since we're dealing with reactive mixtures, we could also rewrite this dNi in terms of the stoichiometric coefficient and the extent of reaction. Okay? So we have ds is equal to, we'll keep the negative around, I is equal to 1, c, mu I, nu I, d epsilon. Okay? Alright, so we have this here. We have this statement. And if we go back here, is that in order for a constant NVU system to reach equilibrium, its entropy has to be maximized. And right now in the fundamental equation that we have ds, and we have epsilon. So the canonical variable for entropy here is going to be that epsilon. And so if we kind of sketch out how entropy should change with epsilon, in order for it to reach equilibrium, the system has to reach some sort of maximum at some particular value of epsilon, right? And so that means, if it's going to reach a maximum, that the partial derivative of entropy with respect to epsilon at constant u and a constant v has to be equal to 0. Okay? And constant moles as well. That has to be equal to 0. And so to get that, basically what we do is just move the epsilon over here. And since this is equal to 0, we could cancel out that negative sign. And what we get is that this derivative is equal to 0. And it's also going to be equal to the summation of nu I times mu I. Okay? And so, based on this statement, what this is telling us is that if we take all the stoichiometric coefficients of our reaction and multiply them by their respective chemical potentials and add all those things together, and then that sum equals 0, then that would tell us that our system is at equilibrium. Alright. Okay, and so that's the criterion for constant NVU systems for the reactive system to be at equilibrium.